Let's go back and implement our interpreter now that we take an expression in an environment and return not just an int, but a value. And we can consider all our cases again and see if anything needs to change. So let's look at the integer case. When we have an integer expression n, we have n to work with. But this n is a Shplait integer, right? It's not a capital V value. To go from an int to a value, we use int v. So that's the change compared to the interpreter we had before. Used to be just n, now it's int v of n. How about when we have an identifier? We still can look up in the environment to see what that identifier means, and because we've changed environments so that they have values instead of integers, then we get a value back. So in fact, the lookup case didn't change. It's that we changed the type on lookup and we changed the type of environment to return a value instead of an integer. How about the plus case? We have L and R, and each of those are expressions, so we know to interpret them. Now we get a value back for the left and a value back from the right, which we used to just add, but this addition no longer works because Shplait's plus works on integers, not values. So we will need a new num plus that we write ourselves that takes numbers as capital V values, adds them together, and gives you a number result back. And of course, we're going to need the same thing for multiply. And of course, we're going to need the same thing for multiply. We'll need a num mult. So num plus and num mult helper functions could look like this. We've got values left and right. And we could do a match dispatch here, but it turns out to be easiest to use isa now to check whether left is a int v and right is an int v. Then we can use int v.in to get the integer out of that int v. And now we have two integers. We can add them together and put them back inside an int v. If either left or right is not an integer, that means we're trying to add a function. And in that case, interp can just complain with not a number. Num mult is exactly the same, except we're using times instead of plus. You can probably guess that I made this slide by writing num plus and then copying it to make num mult. And that's error prone, of course. If I had any error up here, now I have twice as many errors. So instead of doing that, I will abstract over num plus and num mult to have num up. The only thing that was different is how we combined the two integers from the left and the right. So I will pass in a function now that we know how to do that. And that function doesn't really need a name. It can just be written inline here in the call to num up. It takes a left number and a right number and adds them together, or it takes a left number and right number and multiplies them together. So this is the definition of num plus and num mult that we'll put in our interpreter. And now we can just use those in our plus key case and multi case. How about let e? Let e turns out not to change because we interpret the right-hand side to get a value back now instead of an int, but that's what bind wants. So we can just bind the name to that value and extend the environment and start interpreting the body. Going on to a function, we have n and the body to work with. Since body is an expression, then the template would suggest that we interpret that expression. But this is a place where the template is wrong, and it's what makes function interpretation interesting. We don't want to interpret that body right away. Instead, a function expression is supposed to return a function value, just in the same way that an integer expression returns an integer value. Function values are written with close v, so instead of terp, we want to use close v here. So close v, its job is to remember the body along with the environment, and we also need to remember the argument name n. And once we do that, it turns out we're all done. Just like we finish an int expression by returning an int value right away, we finish a function expression by returning a function value right away. We just call those function values closures. And then that leaves us with the application case, the function call case. We have an fn expression and an arg expression. They're expressions, so probably we should interpret them. And maybe the environment is just along for the ride here. When we interpret this function expression, we hope to get a function value back. We might get a number back instead. So to distinguish between different kinds of values, we're going to have to do a match to see what kind of value we have. If we don't have a function value, we've got a number value, then in that case we just report an error in the same way that num plus and num mult do. But this time we complain that we didn't get a function as opposed to not getting an integer. Okay, so now we've got a closure v that we got from interpreting the function expression. That gives us an n, a body, and a c to work with. Calling a function means interpreting the body of the function. So this is where we should be going. We should be interpreting the body of the function. What happens to this argument? Well, when you evaluate the argument, you're supposed to bind it to the argument name for the function. So we're going to bind the result of interpreting the argument expression to the argument name and put that into the environment. And then finally, which environment is it that we extend? We have two choices, it seems. We have the environment that we've been working with, but we also have this environment for the closure. And remember, the environment for the closure is all the things that should have happened to this body. Since we're interpreting that body, then we want to use that environment, not the other one. Right? So this is a key part to get right here, using the environment of the function, not the environment where we happen to call the function, which is what EMV is. When you put these pieces into the full interpreter, then we've got our parser there, but now we have the interpreter with the code we just saw on the slides. We've got these tests, and you'll notice that all the tests now have int v's for the old test, and we have a close v for our new test on parse of fun, and we have some other function calls, and we have these error cases to check. One where we expected a function, one where we expected a number, and so on. We've got the num plus and num mult functions here, implemented in terms of num up, and lookup is the same as it was before. Just now we've updated the lookup examples to use int v's instead of plain integers. One thing you don't see is anything to do with parsing function definitions. We just have parse on expressions. And you don't see a list of definitions passed to interp. We don't have to do that anymore because everything is covered by the environment by using let to bind function names.